Okay, let's go ahead and get started. Hi, all, and welcome again to the bi-weekly Green Bank Observatory Community Zoom. Thank you all for taking some time in your day to learn a little bit about some awesome science going on with Green Bank Observatory. As I'm Karen O'Neill, I'm the director here, and as always, we'll start off first with me giving you just a very brief highlight about what's going on with the observatory, and then we'll hand this off to our main presentation, which is Nissim Kanekar talking about H1 and the Green Pea galaxies. So what's going on with Green Bank? As always, it's a microcosm of what you see around the United States. Right now, very much unfortunately, what we're seeing is that the number of COVID-19 cases within the state of West Virginia is rising much more rapidly than the number of vaccinations within the state of West Virginia. So you can see Pocahontas County has had 13 new cases of COVID-19 this past week. So that's unfortunate, and we can just hope that the number of vaccines continues to go up. The good news, though, is again on site, we're seeing return to work. We've got more than 95% of our staff are vaccinated. Just a few folks aren't yet for a variety of different reasons. Staff are coming into work, and our health checks are in place. So all of that's going very well within our very microcosm of Green Bank Observatory. Site itself, of course, remains in full operations 24 hours a day. Our science center has reopened. We've got our bus tours, we've got our exhibit halls, all of that's going fantastically. Masks are, of course, required there just because that way we don't have to worry about things like the Delta variant as much and just keep everybody safe. Visitors are also coming back on site, which is great. If you're coming back on site to visit for many of our activities, to workshops, observing things like that, we can absolutely do that. It does require the FDA approved vaccination in advance and, of course, advance notice so that we can make sure we have a space for you and a plan for you here on site. But it's nice to start seeing faces again. We're very happy about that. Additionally, this week, we have all of the vaccinated Green Bank Observatory and NRAO summer students here on site, getting a chance to finally have a little bit of face-to-face interaction and giving their talk, showing us all the absolutely amazing work, research that they've done over the summer. So that's been a huge amount of fun just to hear about all the wide variety of different projects going on. Emphasize again, we do have a number of job openings here at Green Bank Observatory, just a variety of different positions due to retirements and other things. We've got software and electronics engineers. Our current telescope operating division head is still open, apprenticeships and so forth. So I encourage you, if you're interested in coming to be part of the absolutely fantastic Green Bank Observatory team, to take a look at our website and look at the possible job openings that are out there. Finally, of course, we're continuing these community Zooms. So we've got the next three are listed here. In 2 weeks, we've got Michael Bush talking a lot about some faint OH emission going on in H2 areas of the galaxy. And then our own Charles Romero looking at the thermodynamics of galaxy clusters. And then finally starting to look at I've got Charles's talk on there. We've got Emmanuel Fonesca from West Virginia University on September 15th, not giving the same talk as Charles, but of course giving a talk on his own research. So sorry about that. So with that, I'd like to also remind you, last thing, that the single dish observing training workshop signups are going on. That will be hybrid, in person, and remote with all of that. So with that, I will hand this off to Jay now to introduce today's speaker. So it's all yours, Jay.
Okay, thanks, Karen. Yeah, our speaker today is Nissim Kanekar from the Tata Institute of Fundamental Research, and he'll be talking about H1 in Green Pea galaxies. And let me just remind you, if you are new to these webinars, that we take questions through the Q&A button in the lower right-hand part of your screen, and I'll be moderating the questions at the end. Take it away, Nissim.
Great. Thank you, Jay. Can you see my slides?
Yes.
Great, thank you. Right, so I'm going to be telling you about some work we've done with two of my favorite telescopes, the Arecibo telescope and the Green Bank telescope, looking at the H1 21 centimeter line in fun galaxies called Green Pea galaxies. And these two, the two images down below are made by James Rhodes, one of the collaborators. Essentially dishes full of green peas, which I will recommend to you for your consumption, if nothing else, for the next 15 minutes. So why should you care about green pea galaxies? And the reason you should care about green pea galaxies, besides the fact that they're interesting by themselves, is that we believe that the universe was reionized at redshifts larger than about 6 by far ultraviolet photons from star-forming galaxies. And that's the last phase transition that took place in the universe. And we believe that phase transition was driven by photons from star-forming galaxies, not from active galactic nuclei. And the problem is that, of course, that these galaxies are relatively small objects. They're early in the universe, and it's very hard to observe them directly since they're really far away. And we don't quite understand how the ionizing photons, what are called the Lyman continuum photons, escape from these galaxies. How do the far ultraviolet photons, which reionize the universe, escape from these galaxies? And it's a pain to study these galaxies directly. They're just too far away. So what people have been doing over the last decade or so is to try to study local analogs of the epoch of reionization galaxies, which, because they're in the local universe, in the nearby universe, can be observed with our best telescopes, and it gives you access to much, much more information about these objects. And the beauty of Green Pea galaxies is that these appear to be, at least today, the best low redshift analogs of EOR galaxies. So if we can understand the physical processes that govern Green Pea galaxies, we should have a good understanding of what actually happens in EOR galaxies. So what are Green Pea galaxies and why are they called Green Pea galaxies? So the image in the bottom left is an optical spectrum from the Sloan Digital Sky Survey of an example Green Pea galaxy. And what you see over here, so look at the scale over here. It goes out to about 1800 or so in these funny units. And on the right, you see a normal galaxy, a main sequence galaxy. And you see the scale is completely different. It goes to about 15 or so. So this is about a factor of 100 larger in the optical spectra. And what you see is that the optical spectrum of this Green Pea galaxy is dominated by this line over here at about 5,000 angstroms, the doubly ionized oxygen triplet line. And it's also got fairly strong H-alpha emission, Balmer alpha emission. And the oxygen 3 line, the oxygen, the doubly ionized oxygen line is much stronger than, for example, the singly ionized oxygen line. While if you look at the main sequence galaxy over here, you'll see the oxygen 3 line is actually fairly faint. The O2 line, the singly ionized oxygen line, is actually brighter than the O3 line. And the H-alpha line is brighter than the O3 line. And so Green Peas are special because their O3 lines are so powerful. And in fact, this caused them to be called Green Peas. When people were looking at these with the SDSS about 12 years ago, citizen scientists from the Galaxy Zoo project, this line gets redshifted into the R band for objects at a redshift of about 0.2, 0.3. And that bumps up the flux density in the broadband filter of the SDSS in the R band. And when you're making these false color images of galaxies, the R band gets mapped to green. And so these objects look like they were green objects, and they look really compact. And so the citizen scientists of this project basically call them Green Peas, and that name is stuck. I think it's a pretty good name. But what makes them special is that they have these spectacularly powerful spectral lines in the optical, especially the oxygen 3 line, and we'll talk about that a little more later in the talk. So what are Green Pea galaxies? Green Peas are basically extreme emission line galaxies at relatively low redshifts less than 0.3. And they have, as I said, powerful O3 5007 angstrom emission. They stand out in their O3 emission. What is interesting, though, is that people have used the Hubble Space Telescope, the Cosmic Origin Spectrograph on HST, to observe the Lyman alpha emission of these Green Peas, of a bunch of Green Peas. And what has been seen is that they have extremely strong Lyman alpha emission. But even more interesting, if you look at the distribution of Lyman alpha equivalent widths of Green Peas, they're very similar to the distribution of Lyman alpha widths in high redshift galaxies, like the galaxy that reionize the universe. The other strange thing is that if you look at the HST images of these objects, they look like, to use the technical term, train wrecks. And this shows you a bunch of HST images from Young et al. 2017. And there's nothing that you can really pick out in these objects. They don't look like nice disk galaxies or anything. They just look like a mishmash. And the scale over here is really small. It's 3 by 3 arc seconds. So the emission in a near ultraviolet is coming from a tiny little region. In fact, you'll see in a second, the near ultraviolet size is less than a kiloparsecs, much less than a kiloparsec. The median size is about 0.3 kiloparsecs, which is tiny. So the young stars are forming in a very tiny region in the center of the galaxy. And these objects have high star formation rates. They have really low stellar masses. They have low metallicity. and they have low dust content, and they have a high ratio of O3 to O2. And all of these are very characteristic of the early galaxies that we believe reionized the universe. So that is indicative that these might be good analogs of high redshift galaxies. But the smoking gun signature that makes Green Pea so interesting in terms of being an analog of high redshift galaxies is that these objects actually show Lyman continuum leakage. So again, Hubble Space Telescope observations of Green Peas at a redshift about 0.3 have actually found direct evidence of Lyman continuum coming out of these Green Peas, especially work by Izotov and collaborators, at the level of a few percent to about 70%. So somehow the Lyman continuum comes out of these Green Pea galaxies. And what Izotov et al. Also found was that you see a higher leakage of the Lyman continuum for higher ratios of the O3 to O2 equivalent widths. So all of this is very interesting, and we'd love to find out what's going on in these Green Peas. So they're clearly starburst galaxies, and they have these fairly interesting properties. And so we have a lot of information about Green Peas in the optical and in the ultraviolet with HST observations. But unfortunately, we have, until recently, no information at all on the neutral gas, either atomic hydrogen or molecular hydrogen. Molecular hydrogen is hard to trace. The CO lines are hard to detect in Green Pea galaxies because of low metallicity. But atomic hydrogen should be, you'd imagine, detectable, except that these objects are really small in their stellar mass. And the reason atomic hydrogen, H1, is interesting is, of course, that you need H1 and later H2 to fuel the starburst in Green Pea galaxies. But the problem is that if you want the Lyman continuum to escape and the Lyman alpha to escape, you also need to have a low atomic hydrogen column density. So there is a tension between having enough hydrogen to fuel star formation, but having a low enough hydrogen column density for Lyman alpha and Lyman continuum to escape. And that's been one of the conundrums for Green Peas. And of course, we've had no data on the subject. So the two questions that we'd like to answer with regard to Green Peas are, first, what causes the starburst in Green Peas? Why are Green Peas these extreme starburst galaxies? And second, and this connects really to the high redshift universe, how do the Lyman alpha and Lyman continuum escape from Green Peas? So what we did was that over the last couple of years, we used the Green Bank telescope and the Arecibo telescope to carry out H1 21 centimeter spectroscopy of about 45 Green Pea galaxies at relatively low redshifts less than 0.1. And these are picked to be fairly uniformly sampling the sample of the large Green Pea sample of 1,000 Green Peas of Jiang et al. 2019. And we were really happy to detect 21 centimeter emission for the first time in Green Peas. And remarkably, about half the sample showed detections. We had 19 detections of 21 centimeter emission and about 21 upper limits on the H1 mass. 5 objects had their 21 centimeter line wiped out by interference, so we couldn't say very much about them. But about 19 of the 40 gave us detections. And the detections were all over the place. The spectral lines, I'm not going to show you any spectra. I'm going to simply jump to the results. The H1 mass spanned a wide range, about a factor of 100. It went from about 4 times 10 to the 8 solar masses to about 3 times 10 to the 10 solar masses. And the median seemed about normal, about 3 times 10 to the 9 solar masses. And the non-detections went from about 6 times 10 to the 7 solar masses, the 3 sigma upper limits, to about 3.2 times 10 to the 9. The median upper limit in the non-detections was about 5.5 times 10 to the 8 solar masses, fairly low upper limit of the H1 mass. And the line widths were not particularly special, between 30 and 400 kilometers per second, with larger line widths for the higher mass galaxies. And the median width was about 120 kilometers per second, which seems a little high for given the low stellar mass of the galaxies, but not terrifyingly so. So let's jump straight to the results, and we try to put these Green Peas in the context of other star-forming galaxies in the nearby universe. So the first thing that we did was that we simply took the ratio of the H1 mass of the Green Pea sample to the stellar mass of the sample and plotted that against the stellar mass. And what you see over here, so this is in log units. So 0 over here is where the two are equal. 1 over here where the H1 mass is 10 times the stellar mass, and so on. And what you see over here is that the blue points, so the blue points of the blue curve are median values from the XCAS sample of Barbara Catinella and collaborators And that's basically a stellar mass selected sample, which goes down to about 10 to the 9 solar masses in stellar mass. And what you see is that the ratio of H1 mass to stellar mass kind of increases as you go to lower and lower stellar masses. And the green stars over here are the medians of the green peas. And you can see that at 10 to the 9, the green pea star is bang on the X-gas star. And you can see that at about 10 to the 8, it seems like a smooth extension of the X-gas trend. And so it looks as though the median gas to stars ratio in green peas is bang on the X-gas sample. But if you peer at this a little more closely, you'll see something interesting. You see that most of the detections of the green peas are sitting up here above the trend of the X-gas sample, while most of the non-detections are actually sitting below the trend. There are a few, of course, there are a few non-detections which are on the trend or just above it, and there are a couple of detections which are below. But broadly, the detections lie above the median and the non-detections lie below. So there is this kind of hint of a bimodality in the green pea population. And if you look at the same thing, at a similar thing, where instead of taking the ratio of the H1 mass to the stellar mass, you plot the ratio of the H1 mass to the star formation rate. And that's called the H1 depletion time. It's basically the time scale on which the atomic hydrogen would be consumed by star formation if the star formation rate were constant over this period of time. And again, I've plotted the X-gas median over here, and that's about something like 7-8 billion years. So it's, this horizontal blue line is the X-gas median, and the green pea median is lower by an order of magnitude. It's about 0.6 gigayears. But again, you see an interesting fact that most of the detections of the green peas are actually not very different from the X-gas sample. Some of them are lower, but most of them are at least in keeping with the X-gas depletion times. So it's true that green peas are forming stars really rapidly, but some of them at least seem to be at least consistent with the X-gas medians. But many of the non-detections, the upper limits on the depletion time are much lower than the median. So again, what this is telling you is that there's a hint of bimodality, but the take-home message of this is that green peas will exhaust their H1 very quickly compared to normal star-forming galaxies. The amount of H1 that they have is not enough to fuel the star formation for more than about a gigayear, much less than a normal galaxies. So that's one take-home message immediately. The next plot over here is a plot of the H1 mass of green peas against the absolute blue magnitude. And in the local universe, a variety of studies going back to the 80s has shown that the H1 mass is tightly correlated with the absolute blue magnitude of a galaxy. And the solid dashed line over here shows the relation in the local universe. And the two dotted lines over here show you the plus and minus 2 sigma spread around this relation. And what you see again is that the green peas broadly sit around this relation. In fact, the median sits bang on the local relation. But you again see that there's a whole bunch of points over here which are above this 2 sigma spread of the local relation. And there are a bunch of upper limits to the MH1 MB to the H1 mass, which are below the 2 sigma spread. So more than 30% of the green peas lie outside the plus minus 2 sigma spread of this relation. Again, a hint of bimodality. Again, curiosity, if nothing else. And finally, if you plot the H1 mass against the ratio of O3 by O2, which I've called O32 over here, and this again on the log scale, so that's a value of 10, you find that most of the detections are at relatively low values of O32. And there are essentially no detections at O32 values larger than about 10. So there are a few detections at about 10 and nothing at all above 10. And this kind of is consistent with the notion that you see higher Lyman continuum leakage at higher O32 values. These objects seem to have lower H1 masses than these objects. And that might make sense that it'll be easier for the Lyman continuum to leak out. But I should mention that even at O32 values of about 10, you do see Lyman continuum leakage. So this is still, it's not clear, it's not quite clear what's going on over here. There's certainly a fair amount of H1 you can see in these 6 galaxies over here, which have reasonably high O32 values going out to about 15 or so. So that's a quick summary of the talk. So these are essentially the first measurements of the H1 masses of green peas. Of course, they're possible only because of the wonderful sensitivity of the GBT in our Arecibo. And so we've detected about half the sample. And we're finding a bunch of curiosities. The first one is that the median gas to stars ratio is consistent with the X-gas sample. The detections are typically above the median. The non-detections are typically below the median. And there's a hint of bimodality in this relation. The H1 depletion time scale is extremely short. It's an order of magnitude lower than X-gas in the median. And again, the detections seem to be consistent with X-gas, although maybe a little bit below. But the non-detections are more than an order of magnitude lower than the X-gas sample. Similarly, the MH1-MB relation in green peas, the median relation is broadly consistent with the local relation, but more than 30% of green peas are plus minus 2 sigma deviant from the relation. Some of them are above the relation, some of them are well below the relation. Again, hint of bimodality. And then there are relatively few 21 centimeter detections at high values of the O3 by O2 ratio. And this is consistent, as I said, with a higher Lyman continuum leakage at high O3-2 ratios. So what all this is telling us is that it's possible that what the data seem to be telling us is that green peas may have a bimodal H1 distribution. They have a fair amount of H1 and almost no H1. And what's probably happened in the systems which have no H1 right now, or upper limits in the H1 mass, is that the neutral gas has been very rapidly eaten up by the process of star formation. There's still star formation happening. There's probably still molecular gas which is feeding the star formation, but the H1 has mostly been eaten up. And it looks as though the Lyman continuum and Lyman leakage might arise from the most gas-poor green pea galaxies. And so this now we can test by actually going out and carrying out HST spectroscopy of the green peas of our sample. And the prediction is that the Lyman alpha, we can observe Lyman alpha in all of these objects. You would expect to see stronger Lyman alpha in the objects which don't have much H1. And of course, in addition, we can go ahead and map the 21 centimeter emission with the GMRT and the Jansky very large array. And that's what we are doing right now. So I think I'll probably stop here since I think I've eaten up 15 minutes and take any questions that you might have.
Thank you very much for a most interesting talk. And I'd just like to remind all of the listeners to submit your questions through the Q&A button on the lower right. And we have questions arising already. And here's the first question. Is there any relation between H1 content or depletion time versus metallicity within the sample, the green pea sample?
That's a good question. There's not much of a relation between H1 depletion time and metallicity, and you can kind of see that over here because you can see there's not much of a relation between depletion time and the stellar mass, and the stellar mass is correlated with the metallicity. And so the fact that the depletion time is kind of flat, from 10 to the 8 in stellar mass all the way out to 10 to the 10 thereabouts, is telling you that there's not much of a trend with metallicity either. But you could also plot this against metallicity and you would see that there isn't much of a trend.
Okay, another question. What could be the progenitors of these green peas?
Okay, if you like, I can show you something interesting, which is the first mapping of a green pea with the GMRT. And that's over here. So, and that's a system which actually violates everything that I told you a little while ago. We actually have an HST cost spectrum of this from McKinney et al. And you see really strong lamina alpha emission in the green pea. It's got a high O3 by O2 ratio, about 8.8. But with the GBT, we see this beautiful H1 emission line. And it's got this high H1 mass. So it's a gas-rich galaxy, but it's still got lamina alpha emission. So we went off and mapped it with the GMRT. And this is what we saw. So you can probably barely, so these are 4 images of the 21 centimeter emission at 15 arcsecond resolution, 12 arcsecond, 9 arcsecond, and 7 arcseconds. And what you see is that even at the lower resolution image, 15 arcsecond, let me remind you that the Green Bank telescope beam is about 9 arc minutes. It's much bigger than this. All this emission is within the Green Bank telescope beam. But because the GMRT is an interferometer, we can actually map the emission. And what you see is that there's actually 2 points over here, the green pea, which is at the center of the image, and then there's a second black point, which seems to be close to the center of this red emission. So the red emission is where is the strongest 21 centimeter, and green is fainter. And that second point over here is another galaxy, which is about 5 kiloparsecs from the Green Pea. And as you go to higher and higher resolution, you can see that the emission is actually in the ring around these two galaxies. And when you go to the highest resolution, 7 arcsecond, you'll see that the brightest emission is actually not from the second galaxy. It's between the Green Pea and galaxy G1. What's happening is that the two galaxies are hammering into each other. They're just normal galaxies, but they're actually undergoing a merger. And that merger seems to be compressing the emission in the H1 in the gap between the galaxies, and it's triggered a burst of spectacular star formation in the Green Pea. And this is what we think is going on. So they're probably normal galaxies, but at least the ones which are H1 rich, but have actually undergone a spectacular merger recently.
Thank you. Here's another question. Can you comment on the molecular content from, for example, CO observations, which might be more relevant to star formation?
Sure. So unfortunately, I can't comment on the molecular content. There have been no observations of CO in Green Peas. We're planning to put in a proposal to ALMA in the next cycle. We're looking forward to that. We would love to map the CO in these objects. It's hard because the metallicity of Green Peas is small, but we have a sample that we think we can go after. So watch this space a year from now.
And also, any idea about the star formation efficiency?
So the star formation efficiency is essentially, it depends on how you define star formation efficiency. The star formation efficiency is usually or often defined as the inverse of the gas depletion time. So it's simply the inverse of this quantity over here. And so star formation efficiency is much higher in Green Peas than in, say, normal X-gas-like galaxies.
Okay, have these galaxies been observed in X-rays?
There have been a few observations, about, I think, 4 or 5 observations, and a couple of them have been detected. So that's an area, that's a very good question. It's an area in which I think a lot of work is going to happen over the next few years.
Let me just comment that the idea that these are colliding systems certainly makes sense in view of the very small region from which you're seeing emission and the large line width in the H1 lines, which suggests a much larger object.
Yeah.
And in which case, I'm wondering whether the depletion time makes any sense, really.
Exactly. So that's a good question. The depletion time over here is simply, it's simply taking the total amount of H1 and dividing that by the total star formation rate. And so in reality, for example, if you look at this galaxy, there's almost no H1 at high resolution coming from the Green Pea. Most of the H1 is all the way around it, but the bulk of the star formation is happening at this very tiny location right here. So I agree. It's a way of quantifying the amount of gas that's available for star formation. But you can see from this image that because there's almost no H1 over here, even this galaxy, which has a relatively high gas depletion time, relatively, because it's got a high H1 mass, in reality, the H1 in the galaxy itself is really small. So so once we map the H1 and we can actually measure the H1 mass in each galaxy individually, it'll probably tell us that these galaxies actually will eat up the H1 much, much quicker than we'd anticipated from the single dish observations.
And there's a related question on how much contamination from companions could be an issue in the single dish measurements.
Exactly, yeah. So that's the reason that we want to do these mapping observations. In the optical, there's not strong, some of them have companions identified in the optical and which have spectra, but not too many. I think about 4 or 5 of them had SDSS companions. But, and so that's why we're very interested in what the H1 shows. Or there could well be contamination from objects which are not heavily star forming themselves.
Mm-hmm. Here's another question. Have you tried to correlate the escape fraction of Lyman continuum or Lyman alpha of these galaxies to the amount of H1?
Yes, and we don't have, so for example, in this object, so we expected to begin with that the Lyman alpha escape fraction would be high when you had objects which had, for low H1 masses. And that's kind of, so we have about 20 objects which have both Lyman alpha emission and H1 spectroscopy. And there's about 10 of them which don't show H1 emission and which have clear, strong Lyman alpha emission. or which have strong H1 emission and no Lyman alpha emission. The Lyman alpha is an absorption. And that makes sense. That's a nice correlation. But you also see objects like this one, where you have strong Lyman alpha emission, but also strong H1 emission. So this has a Lyman alpha escape fraction of about 11%, which is fairly high. But you also see strong H1 emission. And the problem is exactly this, that if you look at the green pea, there's not much H1 in the green pea itself. And so Lyman alpha escapes from here. So we really need the mapping observations. So now we have mapping data for about 10 of the green peas. And so over the next 6 months, we hope to reduce all the data and get an answer to this question.
And a related question, what's the origin of the very broad Lyman alpha absorption? Do the 21 centimeter emission data provide any insight?
So the breadth of the Lyman alpha absorption, that's basically a damped absorption line. And so you mean the absorption line, right? Not the emission. It's this line that you're talking about over
Yes.
here. Yeah. So that's just those are the damping wings of the line. But actually, this is it's probably so there's probably damping wings coming in, but there's also emission which is leaking out. There are probably holes, I would think, in the H1 from which the Lyman alpha is leaking out. Normally, you would expect these kind of wings to only be seen if the flux goes to zero. So you'd have these really wide damping wings. But I think what's happening is that there's enough leakage of the Lyman alpha of the continuum around the H1. And so therefore, you're not seeing it going to zero. That's a hunch. I won't bet a large amount of money on it. But you do see similarly really wide absorption lines when you don't have this strong Lyman alpha emission. So I think this is leakage, but I wouldn't bet large amounts of money on it.
Okay, there are other questions. We have time just for one more. Given the compact size, relatively gas richness of these galaxies, and the possibility of a merger for their origin, do you know if the rate of dwarf mergers at low redshift agrees with the green pea number density?
That's a good question. I don't think we have a really good answer to that as yet. We're looking at it. These are certainly, there are a few similar galaxies in the relatively nearby universe, less than 0.01, but the numbers are small. So we don't, there are not too many spectacular dwarf starbursts in the very nearby universe. For example, there's a famous galaxy called SPS 0335 minus 0022, I think, or minus 22, I can never remember. But that's an example of a dwarf starburst which has properties very similar to green peas. But there's not too many of them.
Well, I'm afraid we're going to have to bring this fascinating exchange to an end. Thank you very much, Dr. Kanekar, for your presentation. I'd like to remind everyone that this presentation has been recorded and within a few days will be uploaded, and you'll be able to access it through the Green Bank Observatory website. 2 weeks from now, we will have Michael Bush talking about the galactic distribution of dark molecular hydrogen in the Milky Way based on OH observations with the GBT. We look forward to seeing you then. Goodbye.